Now, there are a couple of important takeaways that I want to make sure that we discuss now that we've introduced where this idea of a definite integral comes from. The first is that no matter how we encounter the integral, and as you move through calculus, you'll discover definite integrals in lots and lots and lots of applications, just the way that when you see a derivative sign and you learn in your head to think about that as slope, it's a really good idea to see an integral sign and think of an infinite sum corresponding to that. Okay, I'm looking at an infinite sum of something. What is it that I must be adding up? That mentality and that thought process regarding integrals is a really good idea to carry through the rest of your study of calculus. In our particular example, the things that we were adding up were areas. Another thing I like to point out is that a common calculus mistake among early students is to see the dx in the integrand of the integral. For the record, the things that are being added up as pictured over here in this expression are called the integrand of the integral. And as I was saying over here, a lot of students forget the dx that is pictured right here, and they very much like to just write their integral from a to b of the function f of x, and they totally omit this part of the expression. Both of the pieces, the f of x and the dx, truly have a meaning, and so it's important for that dx to be there. The dx is really representing the width of the rectangle. And so it does have a physical meaning and a reason as to why it's part of the integrand, other than just an annoying notation we need to leave when we're writing things down. So that's a point that I like to make clear. The dx represents the base length of our rectangle, while the f of x portion is representing the height. And both of those pieces are equally important in determining the area of a rectangle. Now, the third thing that I'd like to really point out is that very technically, we have not created an equation for the area between a curve and the positive x-axis. What we've actually created is an equation for what's called the signed area between that curve f of x and the x-axis. And there are actually two different issues going on here that I'd like to discuss. So first of all, in the example that I chose when introducing the definition of this definite integral was a very nice example where our curve f of x was always drawn above the x-axis here. So this f of x piece, which we were using to represent the height of the rectangle, was a positive number because it lies above the x-axis. It's perfectly possible to have a curve f of x over here that has values that dip below the x-axis. And in the equation that we put rectangles between the x-axis and the curve, when that function f of x is negative, if we use the value of f of x to represent the height of that rectangle, but f of x is a negative number, then this b minus a over n part is going to be a positive number. This f of x value is going to be a negative number. And so we're not actually going to be returning the positive area that we have right here. What we'll be getting is the signed area, a negative expression whose absolute value is equal to the area of this rectangle. That's a very good thing to be aware of, because what it tells us is that it's very possible to compute the value of a definite integral and get a negative number or get 0. And what those values are meaning when we're getting negative output from a definite integral is that we have more area beneath the x-axis on that interval from a to b than we have above the x-axis on the interval from a to b. And so there is a meaningful interpretation of a negative sign in a definite integral. Whereas if we were just talking about area and we were doing a pure area computation and we got a negative number, we should have alarm bells going off in our head. But in the context And according to the way that we've defined our definite integrals, negative signs are actually okay. Another thing that's actually signed was that dx value that we introduced. In some ways, and I've put this in quotation marks, our dx value can be negative. Again, be negative in quotations. So what do I mean by that? Again, I chose a picture where I put A as an endpoint over here and B as an endpoint over here. And my A value was less than my B value. So when writing down this expression B minus A, I'm getting a positive number right here and dividing it by n. However, when I write something like this down, start at A and stop at B, there's really no mathematical rules to what I could write on a sheet of paper as to why this A value would need to be smaller than this B value. So it's very possible that we could see a definite integral with a larger number down here and a smaller number up here. If the numbers that we put here and here actually have the A value being larger than the B value, then when we perform this computation, B minus A, I'm going to get a negative number here, and this whole expression dx will evaluate to something negative. What's kind of interesting about that is that if we consider the difference in the definite integral of the function f of x from a to b versus the definite integral of f of x from b to a, what each of those things would mean, according to the definition on our previous slide, is that this integral would translate to some sort of limit of sums, that part's not important here, of integrand f of x times b minus a over n, while this expression over here would evaluate to some sort of limit of sums of the function f of x times the quantity a minus b over n. These two expressions are nearly identical, but not exactly the same. And in fact, what we need to do in order to relate our left-hand expression to our right-hand expression is multiply this dx value, b minus a over n, times a negative 1, which will make the b negative and the a positive exactly as it appears over here. And so you'll often see rules written down in calculus books about definite integrals, and one of the rules that you frequently see is this rule right here, which says if you take a definite integral and you interchange the bounds, instead of integrating from a to b, you integrate from b to a, you'll get the same result with a minus sign in front. The reason that this rule exists is because of this definition. The dx in the left-hand side integral needs to be multiplied by a negative 1 to turn into the dx of the right-hand side definite integral, and that's the reason for this relationship.